Quantum mechanics is mind-boggling. If you think you understand quantum mechanics, you don't understand quantum mechanics. If along the way quantum mechanics seems to be a little bit bizarre, or even altogether ludicrous, you should bear in mind two things. First, beyond the fact that it's a mathematically coherent theory, the only reason we believe in quantum mechanics is because it yields predictions that have been verified to astounding accuracy. If someone can tell you volumes of intimate details about your childhood in excruciating detail, it's hard not to believe their claim of them being your long-lost sibling. Secondly, you're not alone in having this reaction. It's a view held to a greater or lesser extent by some of the most revered scientists of all time, including a little-known scientist called Albert Einstein. Even Einstein refused to accept quantum mechanics fully. And on that pessimistic note, let's start this video on quantum mechanics. Quantum mechanics is a conceptual framework for understanding the microscopic properties of the universe. And it all started with something called the infinite energy paradox, or the ultraviolet catastrophe. Early calculations implied that a hot body or an object such as a star must radiate energy at an infinite rate. According to the laws we believed at the time, a hot body ought to give off electromagnetic radiation equally at all frequencies. For example, a hot body should radiate the same amount of energy in waves with frequencies between 1 and 2 million waves a second, as in waves with frequencies between 2 and 3 million waves a second. Now, since the number of waves a second is unlimited, that would mean that the total energy radiated would be infinite. In order to avoid this result, the German scientist Max Planck suggested that light and other waves could not be emitted at an arbitrary rate, but only in certain packets that he called quanta. Moreover, each quantum had a certain amount of energy that was greater the higher the frequency of the waves, so at a high enough frequency, the emission of a single quantum would require more energy than was available. Therefore, the radiation at high frequencies would be reduced, and so the rate at which the body lost energy would be finite. The energy can be 1 times some fundamental energy denomination, or 2 times, 3 times and so forth, but that's it. Planck suggested that the energy denomination of a wave, the minimal lump of energy that it can have, is determined by its frequency. Larger frequency implies larger minimum energy, and smaller frequency implies smaller minimum energy. Roughly speaking, just like gentle ocean waves are long and luxurious, while harsh ones are short and choppy, long wavelength radiation is intrinsically less energetic than short wavelength radiation. By eliminating the infinite result, Planck had taken an important step. But what really made people believe that his guess had validity is that the finite answer that his new approach gave for the energy in an oven agreed spectacularly with experimental results. Specifically, Planck found that by adjusting one parameter that entered into his new calculations, he could predict accurately the measured energy of an oven for any selected temperature. This one parameter is the proportionality factor between the frequency of a wave and the minimal lump of energy it can have. Planck found this proportionality factor, which is now known as Planck's constant. But importantly, Planck had no justification for his pivotal introduction of lumpy energy. Beyond the fact that it worked, neither he nor anyone else could give a compelling reason for why it should be true. As one physicist said, it's as if nature allowed one to drink a whole pint of beer, or no beer at all, but nothing in between. In 1905, Einstein found an explanation for this through the photoelectric effect. When light or electromagnetic radiation shines on certain metals, they emit electrons. When light strikes the metallic surface, it relinquishes its energy, much as it does when it hits the surface of your skin, causing you to feel warmer. This transferred energy can agitate electrons in the metal, and some of the loosely bound ones can be knocked clear off the surface. The intensity or the brightness of the light source represents the number of photons, and the frequency represents the amount of energy each individual photon has. But the strange features of the photoelectric effect become more apparent when you study more detailed properties of the ejected electrons. At first, you might think that as the intensity or brightness of the light source is increased, the speed of the ejected electrons will also increase, since the impinging light wave has more energy. Rather, the number of ejected electrons increases, but their speed stays fixed. However, the speed of the ejected electrons does increase when the frequency of the light source is increased, and vice versa when the frequency of the light is decreased. In fact, as the frequency of the light source is decreased, there comes to a point when the speed of the emitted electrons drops to 0, and they stop being ejected from the surface altogether, regardless of the possibly blinding intensity of the light source. Einstein suggested incorporating Planck's lumpy picture of wave energy into a new description of light. A light beam, according to Einstein, should be actually thought of as a stream of tiny packets, tiny particles of light that we now call photons. And Einstein used this new conception of light to suggest a microscopic mechanism underlying the photoelectric effect. He proposed that an electron is knocked off the surface if it gets hit by a sufficiently energetic photon. But what determines the energy of an individual photon? Einstein followed Planck's lead, and he proposed that the energy of each individual photon is proportional to the frequency of the light wave. So to actually eject electrons from the metal surface, the frequency of the light has to be above a certain minimum threshold, and the higher the frequency above this threshold, the more energy the electron will have once ejected. When increasing the intensity or brightness of the light source, which means that there are more photons at a time, If the frequency is above the threshold, more electrons will be ejected. But if the frequency is below the minimum threshold, increasing the intensity doesn't impact the electrons and they are not ejected. So then, is light a wave or a particle? More than 300 years ago, Newton proclaimed that light consisted of a stream of particles, so the idea wasn't exactly new. But some of Newton's colleagues disagreed with him and argued that light is a wave. The debate raged, but ultimately experiments carried out by the English physicist Thomas Young in the early 1800s showed that Newton was wrong, and the experiment conducted was a double-slit experiment. Richard Feynman was fond of saying that all of quantum mechanics can be gleaned from carefully thinking through the implications of this single experiment, so it's well worth discussing. So let's start this experiment off with bullets. Here we have a gun that sprays bullets randomly, a wall and a backstop. The wall has two slits where the bullets can pass and hit the backstop. And let's assume this is an idealized experiment, where the bullets don't break and they always arrive whole. When the left slit is open, we expect to see a pattern like this. And when the right slit is open, we expect to see a similar pattern on the other side. And when both slits are open, we observe a pattern that is somewhat of a merger of both of the previous patterns. And the bullets either pass through either the first slit or the second slit. Now, what happens when we repeat this experiment using water waves? When water waves strike the barrier, outgoing circular water waves emerge from each slit, much like those created by throwing a pebble into a pond. As the waves emerging from each slit overlap with each other, something quite interesting happens. If two wave peaks overlap, the height of the water waves at that point increases. It's the sum of the heights of the two individual peaks. If the two wave troughs overlap, the depth of the water depression at that point is similarly increased. And finally, if a wave peak emerging from one slit overlaps with a wave trough emerging from the other, they cancel each other out. This is called constructive and destructive interference, and it leads to an interference pattern. When we do this experiment with light, the wave picture of a light beam tells us that when both slits are open, the photographic plate will look like this. The brightest areas in the picture are where light wave peaks or troughs from each slit coincide. Dark areas are where wave peaks from one slit coincide with troughs from the other, resulting in a cancellation. The sequence of light and dark bands is known as an interference pattern, and the wave result is a lot different from what we observe with bullets or pellets, and hence there is a concrete experiment to distinguish between the particle and the wave pictures of light. Young carried out a version of this experiment, and his experiment resulted in an interference pattern, thereby confirming the wave picture of light. But Einstein, the man who brought down Newton's revered theory of gravity, seems now to have resurrected Newton's particle model of light by his introduction of photons. Of course, we still face the same question: how can a particle perspective account for the interference pattern that we observe? At first, you might make the following suggestion. Water is composed of H2O molecules, the particles of water. Nevertheless, when a lot of these molecules stream along with one another, they produce water waves. And so it might seem reasonable to guess that wave properties, such as interference patterns, can arise from a particle picture of light, provided a huge number of photons, the particles of light, are involved. Even if the intensity of the light source is turned down, finally to the point where individual photons are being fired one by one at the barrier, say at the rate of 1 every 10 seconds, the resulting plate will still show the interference patterns. Now this is astounding. How can individual photon particles that sequentially pass through the screen and separately hit the photographic plate conspire to produce the bright and dark bands of interfering waves? Conventional reasoning tells us that each and every photon passes through either the left or the right slit, and we would therefore expect to see a pattern that we observe with bullets or pellets, but we don't. So let's describe it again, but this time in a different way. You close the left slit and fire the photons one by one at the barrier. Some get through and some don't. The ones that do get through create an image on the photographic plate, dot by single dot, which results in something like this. You then run the experiment again with both slits open. Naturally enough, you think that this will only increase the number of photons that pass through the slits in the barrier and hit the photographic plate, thereby exposing the plate to more total light. But when we later examine the image that has been produced, we find that not only are there places on the photographic plate that were dark in the first experiment that are now bright as expected, there are also places on the plate that were bright in the first run of the experiment which are now dark. By increasing the number of individual photons that hit the photographic plate, we have now decreased the brightness in certain areas. Somehow temporally separated, individual photons are able to cancel each other out. Think about how crazy this is. Photons that would have passed through the right slit and hit the film in one of the dark bands fail to do so when the left slit is opened. But how in the world can a tiny bundle of light that passes through one slit be at all affected by whether or not the other slit is open? As Feynman noted, it's as strange as if you fire a machine gun at the screen and when both slits are open, independent, separately fired bullets somehow cancel one another out, leaving a pattern of unscathed positions on the target, positions that are only hit when one slit in the barrier is open. Such experiments show that Einstein's particles of light are quite different from Newton's. Somehow photons, although they are particles, embody wave-like features of light as well. The fact that the energy of these particles is determined by a wave-like feature, frequency, is the first clue that a strange union is occurring. But the photoelectric effect and the double slit experiment really bring the lesson home. The photoelectric effect shows that light has particle properties, and the double slit experiment shows that light manifests the interference properties of waves. Together they show that light has both wave-like and particle-like properties. The microscopic world demands that we shed our intuition that something is either a wave or a particle and embrace the possibility that it's both. And it's here where we can utter terms such as the wave-particle duality, and we can even translate these words into a mathematical formulism that describes real-world experiments with amazing accuracy. But it's extremely hard to understand at a deep intuitive level this dazzling feature of the microscopic world. Now things get even weirder when we conduct the double slit experiment with electrons. We keep the right slit open and close the left, and sure enough, we see the electrons that pass through are concentrated on the right side of the photographic plate, and vice versa when we open the left and close the right side. But when we open both slits, we observe an interference pattern just like light waves. But the electrons might be interfering with each other, so we fire the electrons one at a time, and when we look at the plate, we still get the interference pattern. This experiment therefore shows that electrons exhibit interference phenomena, the telltale sign of waves. At dark spots on the screen, electrons were somehow cancelling each other out, just like the overlapping peaks and troughs of water waves. And even if the beam of fired electrons was thinned out, for example emitting one electron every 10 seconds, the individual electrons still build up bright and dark bands, one spot at a time. Somehow, as with photons, individual electrons interfere with themselves, in the sense that individual electrons, over time, reconstruct the interference pattern associated with waves. We are inescapably forced to conclude that electrons embody a wave-like character in conjunction with its more familiar depiction as a particle. Now let's try to observe which slit the electron is going through. When we place some kind of detector, we see the electron as passing through one slit or the other, but never both. But now when we take a look at the screen, we see a no interference pattern. So what on earth is going on? It's because now we have changed the experiment. To observe the electron, we must do something to it. For instance, shine light on it, which means bounce photons off of it. Now in everyday scales, photons act as insignificant little probes that bounce off trees, paintings, and people with essentially no effect on the state of motion of these comparatively large material bodies. But electrons are little wisps of matter. Regardless of how gingerly we carry out our determination of which slit the electron has passed through, photons that bounce off the electron necessarily affect its subsequent motion, and it's this change in motion which changes the results of our experiment. If we disturb the experiment just enough to determine which slit the electron has passed through, we observe the results changing from an interference pattern to a no interference pattern. And so the quantum world ensures that once it has been established that each electron has either gone through the left or right slit, its interference between the two slits disappears. And we find that no matter how we arrange the experiment, such as changing the intensity of the light source or changing the frequency of the light, it's impossible to arrange the experiment in such a way that we can tell which hole the electron has gone through and at the same time not disturb the pattern. In order to predict the future position and velocity of a particle, we have to be able to measure its present position and velocity accurately, and the obvious way to do this is to shine light on the particle. Some of the waves of light will be scattered by the particle, and this will indicate its position. However, we won't be able to determine the position of the particle more accurately than the distance between the wave crests of light. So we need to use light of a short wavelength in order to measure the position of the particle precisely. Now by Planck's quantum hypothesis, we can't use an arbitrarily small amount of light. We have to use at least one quantum, but this quantum will disturb the particle and change its velocity in a way that can't be predicted. Moreover, the more accurately we measure its position, the shorter the wavelength of the light that we need, and hence the higher the energy of a single quantum. So the velocity of the particle will be changed by a larger amount. In other words, the more accurately we try to measure the position of the particle, the less accurately we can measure its speed, and vice versa. This is known as Heisenberg's uncertainty principle. No, not that Heisenberg. And it's not just that our measurement requires us to interact with the particle. The uncertainty principle exists alongside this observer effect. It's a statement about how much information we are ever able to extract from a quantum system. This is demonstrated in the single slit experiment, where if we reduce the size of the slit, thereby decreasing our uncertainty of the position of the light, you increase the uncertainty in momentum, leading to a larger spread pattern on the screen. So the electron double slit experiment has shown that particles of matter have a wave-like nature as well, which is a central tenet of quantum mechanics. Before the electron double slit experiment was conducted, Louis de Broglie added a new element to the quantum fray, one that would shortly help to usher in the mathematical framework of modern quantum mechanics. Inspired by a chain of reasoning rooted in Einstein's special relativity, de Broglie suggested that the wave-particle duality applied not only to light, but to matter as well. Roughly speaking, he reasoned that Einstein's E equals mc squared relates mass to energy, and that Planck and Einstein had related energy to the frequency of waves. And by combining the two, mass should have a wave-like incarnation as well. After carefully working through this line of thought, he suggested that just as light is a wave phenomenon, that quantum theory shows to have an equally valid particle description. An electron, which we normally think of as being a particle, might have an equally valid description in terms of waves. Einstein immediately took to de Broglie's idea, as it was a natural outgrowth of his own contributions of relativity and of photons. Even so, nothing is a substitute for experimental proof. And then such proof came with the electron double slit experiment. The electron double slit experiment, conducted after de Broglie theorized this, was proof of matter's wave-particle duality as well. Although we have described this in the case of electrons, similar experiments lead to the conclusion that all matter has a wave-like character as well. But how does this jibe with our real-world experience of matter as being solid and sturdy, and in no way wave-like? Well, de Broglie set down a formula for the wavelength of matter waves, and it shows that the wavelength is proportional to Planck's constant. Since Planck's constant is so small, the resulting wavelengths are minuscule compared with everyday scales. This is why the wave-like character of matter becomes directly apparent only upon careful microscopic investigation. The interference of electrons made the wave-like nature of electrons tangibly evident, but waves of what exactly? One early suggestion, made by Schrödinger, was that the waves were smeared out electrons. This captured some of the feeling of an electron wave, but it was far too rough and ambiguous. When you smear something out, part of it is here and part of it is there. However, one never encounters half an electron, or any fraction for that matter. This makes it hard to grasp what a smeared out electron really is. As an alternative, Max Born sharply refined Schrödinger's interpretation of an electron wave, and it's his interpretation, amplified by Niels Bohr and his colleagues, that is still with us today. Max Born's suggestion is one of the strangest features of quantum theory, but it's supported nevertheless by a huge amount of experimental data. He asserted that an electron wave must be interpreted from the standpoint of probability. Places where the magnitude of a wave is large are places where the electron is more likely to be found, and places where the magnitude of the wave is small are places where the electron is less likely to be found. Quantum mechanics injects the concept of probability into the universe at a very deep level. According to Born and more than half a century of subsequent experiments, the wave-like nature of matter implies that matter itself must be described fundamentally in a probabilistic manner. For macroscopic objects, such as a coffee cup or a roulette wheel, de Broglie's rule shows that the wave-like character is virtually unnoticeable, and for most ordinary purposes, the associated quantum mechanical probability can be completely ignored. However, at a microscopic level, we learn that the best we can ever do is say that an electron has a particular probability of being found at any given location. The probabilistic interpretation has the virtue that if an electron wave does what other waves can do, for instance slam into an obstacle and develop all sorts of distinct ripples, it doesn't mean that the electron itself has shattered into separate pieces. Rather, it means that there are now a number of locations where the electron might be found, with a non-negligible probability. In practice, this means that if a particular experiment involving an electron is repeated over and over again in an absolutely identical manner, the same answer for, say, the measured position of an electron will not be found over and over again. Rather, the subsequent repeats of the experiment will yield a variety of different results, with the property that the number of times the electron is found at any given location is governed by the shape of the electron's probability wave. Exact outcomes of experiments can't be predicted. The best we can do is predict the probability that any given outcome may occur. Even so, as long as we can determine mathematically the precise form of probability waves, their probabilistic predictions can be tested by repeating a given experiment numerous times, thereby experimentally measuring the likelihood of getting one particular result or another. Just a few months after de Broglie's suggestion, Schrödinger took the decisive step towards this end by determining an equation that governs the shape and the evolution of probability waves, or as they came to be known, wave functions. It was not long before Schrödinger's equation and the probabilistic interpretation were being used to make wonderfully accurate predictions. By 1927, therefore, classical innocence had been lost. Gone were the days of a clockwork universe whose individual constituents were set in motion at some moment in the past and obediently fulfilled their inescapably, uniquely determined destiny. According to quantum mechanics, the universe evolves according to a rigorous and precise mathematical formalism, but this framework determines only the probability that any particular future will happen, not which future actually ensues. Many find this conclusion troubling, or even downright unacceptable. Einstein was one of them. In one of physics' most time-honored utterances, Einstein admonished the quantum stalwarts that God does not play dice with the universe. He felt that probability was turning up in fundamental physics. Because of a subtle version, it turns up at the roulette wheel, some basic incompleteness in our understanding. The universe, in Einstein's view, had no room for a future whose precise form involves an element of chance. Physics should predict how the universe evolves, not merely the likelihood that any particular evolution might occur. But experiment after experiment, some of the most convincing ones being carried out after his death, convincingly confirmed that Einstein was wrong. As Stephen Hawking once said on this point, Einstein was confused, not the quantum theory. Nevertheless, the debate about what quantum mechanics really means continues unabated. Everyone agrees on how to use the equations of quantum theory to make accurate predictions, but there is no consensus on what it really means to have probability waves, nor on how a particle chooses which of its many possible futures to follow, nor even on whether it really does choose, or instead splits off like a branching tributary to live out all possible futures in an ever-expanding arena of parallel universes.